Okay, ladies and gentlemen, I would like to introduce you John Fitch with his amazing paper. John?
Yeah?
Please have your word. You're welcome.
Hi. Okay, greeting from sunny Bath. I want to talk about C-SOUND and its multiple use calls. Sorry, I'm getting an echo here. Give me a moment to see if I can fix the echo. Can you still hear me? Right, so on the second slide, right, you can see me now. Right, okay. This is the basic position. The hardware changes mean that we need to have multiple cores. And what I want to talk about is how we can do that within the C-SOUND design. But before that, there's a little comment to be made. On the third slide, just slide 3, please. I once had the privilege of working with Robert S. Barton, and he talked about a thing called the technical imperative. What hardware requires us as a forcing term on software. In fact, with Robert, I worked on parallelism, which didn't work, but we'd learned from that experience. It's always been there with me. Can I have the next slide, Gleb? Next slide, slide 4. That's it. Thank you. So far, that's philosophical remarks. I now want to limit it to C-SOUND. These are the two philosophical positions that I take seriously. The one is that by introducing parallelism, I want no semantic change at all. It's the same system. And the much more pessimistic requirement is that the user doesn't have to change anything. So the ordinary user gets it for free. We'll look and see later how true that is. Next slide, please. This is maybe rude to some of you, but C-SOUND users are typically not software experts. And even software experts get parallelism very wrong. I don't think that users could be expected or indeed trusted to modify their thinking for parallel execution. It's just too hard. And the software system has to take that responsibility. Those are the ideas which are driven behind this whole work. And the next slide, please. The whole design is based on work originally from Jed Marcy at the University of Utah and Ram Corporation. This is actually going back to my tank warfare days, but we don't like to talk about that. The idea is to identify at compile time what can be run in parallel, what can't. Put another way, why can't you run everything in parallel? And the reason is dependencies. The idea behind the C-SOUND model is for the compiler, parser, construct sets of functions of read and write locations, so we could use that to control us. Next slide, please. Yeah. Okay. 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 If we go back to thinking about C-sound and its language, and I was talking about conflicts between variables. The I variables, the P, the K, the A, the F, they're all local to the instrument and therefore cannot cause any problems. It's the global variables which are the real problem. If two instruments, one reads and one writes to a global instrument, we've got to make sure it does it in the right order and correctly. There are other global entities I'll talk about later, tables, ZAC, channels, etc., etc. But at the moment, let's just think about the global variables. Can I have the next slide, please? This should be slide with some little bit of code. Is that right? Right, okay, thank you. This is just a trivial and not very important example. 3 instruments. The first one is simple oscillator. The second one sets a global variable. And the third one reads that global variable. The compiler can then analyze that, as in the next slide, slide 10, to show that instrument 1 is independent of everybody. Instrument 2 must run before instrument 3. And instrument 2 has some sort of interaction if you have multiple instances. The bit saying instrument 1 colon and so on the side is the analysis which the compiler is meant to produce. It's not quite how it's done now, but that's the original design. You must remember that C-sound has a defined semantics. The instruments are run in numerical ascending order. And it's that which we need to preserve. That's the semantics we need to produce. So in this example, instruments 2 and 1 could run on the same time on different cores, but 3 must run after 2, but it could overlap with 1. That's the analysis we need. Next slide, please. This is just to say how you do it. One of the reasons I was very keen to move to the new parser in 5 was so we can actually do this analysis. The parse tree is there, we can read it, we can scan it looking for global variables, build up these dependencies. The real problem are the hidden globals. In the model we had in C-sound 5 got this wrong, or at least not right. Can we have slide 12, please? The first of these is the output. The audio is a hidden global, spout vector, that way of thinking. But the way we treat it is we actually are accumulating values into it. And this statement about not being order, not mattering, isn't strictly true. Apart from problems of rounding error, it doesn't matter which order we do it in, as long as we do it independently of each other. We can't have 2 people trying to update at the same time. This is actually quite easy to achieve by the introduction of spin locks in the out family of opcodes. So the user won't see this, and we can ignore the outs in our analysis. Slight cost if people do try and write at the same time. One of them will be delayed. But that is A, not very likely, and B, the delay is very small indeed. Can I have slide 13, sorry. For tables, acts, channels. This is actually much more problematic. When tables were read-only objects in the original version of CSAN, this wasn't too much of a problem. But now there are opcodes to write, change, modify tables. They have to be table variables or code objects. The solution I've currently got, which I'll talk about later, is each opcode in the structure which says how many arguments it has, inputs and outputs, has to say whether it reads or writes the table. By limiting the changes to the system, access to any table is counted as access to all tables. And this is pessimistic in the sense that if we track which table you're changing, we might get a parallelism revealed. Slide 14, please. Yeah, about the DAG. So this was the big problem in the old model. The DAG, the directed as cyclic graph, the graph which says who depends on what, had to be consumed on every K cycle. And so at the beginning of every cycle, you had to remake the graph. And it meant memory activity, just copying thing. It was actually a huge performance loss. That's the reason I believe that CSAN 5's parallelisms, it delivered sometimes, but really very not enough. In CSAN 6, my co-author, Martin Brain, and myself sat down one day, cup of coffee, and discussed what the problem was. And that's the main part of the new system, what we came up with. Instead of creating the DAG on every K cycle, we only do it when new instruments come in or instruments go away. It doesn't happen very often, relatively speaking, to the computation. So can I have slide 15, please? This is the new model. Martin Brain works in areas of SAT solvers and logic. It worked inspired by working it on that. The main idea is to say, instead of every instrument having a list of who it can't run until they finished, it only has to look at one of them. If it's going to have 5 people before it can run, then it can't run until one of the given one have finished. So the idea is you select that one and watch it. When that one finishes, you look to see if there's anybody else waiting for you. When you do this idea, the whole system can be written about memory activity. It actually uses fixed data size. It's actually 3 or less. It's just one race case. So only when you finish an instrument does this structure need remaking. Can I have the next slide? There were 3 major data sources. For each task, i.e. instance of instrument, you record a state, and there are 4 states. It can either wait some other task to finish. It can be available to be run and waiting for a processor. It can be in progress, meaning it's actually doing things, and it's done when it's finished. There's a second vector, sets of tasks to maintain static dependency, i.e. what the DAG. And there's a vector of lists of tasks that are currently waiting for each task to complete, watch list. This is the big change. Watch list says who is watching me, not who I am watching. So it's the responsibility of somebody when they finish, tell the people watching them that they've finished. No, slide 17. 3 data structures. The task status is just a simple vector of one of those states. Task dependency says who depend on. It must be triangular in that sense because you don't depend on people before you. And the watch list says for each task who's watching them. It looks like there's memory activity there because of the chain of hanging off the watch list. But in fact, there's a finite number of them. Each task can only be watching once. So you have a memory manager which controls those vectors and just moves them around. Turns out to be quite easy code once you realise what's going on. Slide 18, please. If a thread wants work to do, it only has to search the task list looking for an available task. The only slight that is two people looking for work at the same time, they must pick the same one. But that's quite easy with a top compare and swap primitive. Once it's running, you set it to be in progress. That's easy. And GCC helps you do that. If a search fails to find an available task, then either everything's done, in which case you finish the control cycle, or there are still in progress tasks waiting to be finished, so we can loop or use a monitor. I actually loop at the moment because nothing else to do. You might as well just burn the CPU. Slide 19. This shows the actual algorithm. And this really is what the code says, just simplification of writing. Well, for all the number of tasks, look for something which is available. If so, that gives you a task to run. If they're all done, you count how many of them are done and to see when you've finished. That's essentially it. That's all the code really is needed. On slide 20, we look at the problem, what happens when a task finishes. It changes its own status to done. It then walks the watch list associated with it. Everybody watching it, it moves it to an unfinished dependency watch list or marks it as available. I mean, it's hard to explain in the slide, but if you think about it, the mechanism's fairly clear. There is, however, one problem. On slide 21, the second paragraph there, it shows the problem. There's a race condition. Say if two tasks spoke and they're trying to update who looked at, they could actually get a clash with each other. There's a way of solving that using empty value. It's a little bit weird. We are promised a proof that is correct by one of the in Oxford, but we haven't got that proof yet. But not having done the maths strictly, it looks completely right. This is the only part which looks problematic, but it's okay. The condition is benign. Slide 22. This is the thing which is meant to show it really does work. These figures, I think, came from Michael Goggins, so thanking him. We have three works: Cloud Strata, Xanadu, and Trapped, and running on a 4-core machine using 1, 2, 3, 4 cores and normalizing. So times 1. You can see that look at the bottom line of 4 cores, sometimes getting a third of the time. Which is 4 cores delivering 3 times speed up. It's pretty good. If you look at Trapped, however, you notice there is a gain, but the gain really isn't very good. Well, it's a gain, but you notice that 2 cores does as well as 1, as 3 or 4. I think I know why that is, but it breaks my rule about getting the user to change their program slightly. A very small change in trap will give us a large chunk of that back. I'll talk to Rick about that someday. That's the basic algorithm. The rest of the talk is talking about what we could make it better and how it affects ordinary users. So in slide 23, the first comment, this is coarse-grained parallelism. That's to say, the bits that are being done in parallel are instruments, and it performs better if the instruments are heavy. If they do a lot of work, things are better. I have some ideas, not convinced they're going to work, of how to improve this. We could go to parallelism at the opcode level, but I think that the overheads would kill it. So on slide 24 is a small list of how we could make things better. The moment any table change, all tables change, and if we could track that better, same true for channels, we could extract more parallelism out of the system. The coding of that is non-trivial. I've thought about it and it involves a lot of rehashing. The second one is, again, not quite fair, but setting sample accurate and using a large K-sums is quite a good way of doing things. Large K-sums means heavier tasks, more computation before you need to do any checking. And if you look at the table I had before, you'll see that the change in K-sums is what really makes the difference. Really, somebody, me, ought to be writing some guidelines on how to get the best performance. I'd like to collect a bit more data. And there are things which make a huge difference. If you use A equals A plus 1, or equivalent, the analysis, for A being a global variable, the analysis is very pessimistic. But if you use plus equal, the compiler can notice it does that and produce much better code just by using a log. That needs to be written down somewhere more better than it is at some moment. The last part is we have a set of patches for the algorithm which should get slight improvement in performance. I tried it, I think just broke completely. So one day when I get a spare time and a spare mind, I'll see if I can sort that one out. There are some options in there, but they're all fairly heavy work. And the last slide, please, 25. I want to make it clear this is the work of many people. Dr. Jed Marty is somebody I worked with years ago, and a lot of the original ideas in the analysis came from him and his PhD thesis. And Christopher Wilson was an undergraduate in Bath who implemented the version in 5, which got us going. The last two people mentioned, Russell Bradford and Richard Dobson. These are people who I regularly talk to and encourage me and give me ideas. And everybody else who said anything. There's too many people to acknowledge everybody. What I haven't talked about in this talk is the very fine-grained parallelism of things like CUDA and GPUs. That's a slightly different topic and may well make a lot of other things work better. But that's all I really wanted to say. So I think I'll just stop.
Dear John, one. Thank you so much for your very nice presentation. I'm sure there's a lot of questions to you. Yeah? Anybody wants to ask some questions to John Fitch?
John, when are we going to see it? Is it going to be part of C-Sound 6?
It's there.
Or 7?
6. There's an option -J, which sets how many processors you want.
That's right. Yep.
And if your job is the right heavy, you get a gain.
Okay. Any more questions? No. Charmo has his question.
John, thank you. Can you tell what kind of C sound code works better in multiple processes? Can you say any guidelines? What is the good multi-process C sound code?
Sorry, I can't hear properly.
Can you give any guidelines? What kind of C sound instruments or what kind of processing is better for multiple processes?
Do you hear us?
I can hear a few words, but not the question.
Rory will help you. Rory will type you in as a text. Tarma's question as a text. Just a few seconds.
Okay. The answer is anything which does a lot of work. So convolutions in the time domain, fast Fourier transforms, that sort of thing. Simple lookup in oscillators just doesn't give enough. The overhead kills you. Indeed, one of the things I want to do is produce a catalogue of which ones do what. That's not really a very good answer.
Thank you. Thank you. So, thank you, John Fitch. Thank you. Thank you. So, and now I would like to give word to Ian McCarthy, right? Yes? Oh, actually, Victor is calling. Maybe we should answer. Victor? Ian McCarthy, right? No, actually it's me, Gleb, but time slot for Ian. But maybe since we have you here and you already connected, probably
Hi, Rory.
we could give word to you. Yeah.
Just turn it off.
Victor? Oh, yeah. Victor? Do you hear us? I guess with some delay. Yeah.
Can you hear me?
Okay. So, Ian, is it okay to make Dr. Lazzarini presentation first? Okay. Dr. Lazzarini, you have your time. Please welcome.
Can you hear me? Okay, I'll share the screen now. Wait for a minute. Just give me 1 minute and I'll get going. Right. Now, can you see it? Right? Now you have to tell me, can you see the screen? Okay, let's go. Okay, so my talk today, I'm just a minute here, put the volume down for a minute. Okay, my talk today is about defining the craft of computer music. So it's going to be a little bit different from the previous speakers. Basically, my idea with this talk is to to provide a background to the whole idea of teaching computer music, and also what we should expect from computer music if you are, for instance, someone who's starting there. Okay. Oh, this is not going good. Just give me a minute. I'll just change PDF viewers. Just give me 1 minute. Okay, that's better. Excellent. Okay, so do you want to be a composer? Now, this is just a little here for you. So when I was about 15, okay, I took a course in composition, and this summer course had a very well-known teacher, a very well-respected composer, and he asked me if I wanted to be a composer. Okay, I said yes, I'd like to be a composer. Okay, then he sent me down to one of his assistants, and then I spent the whole course doing species counterpoint. So, do you want to be a computer music composer? That's the question. So what is this talk about? This talk is concerned with trying to define what discipline of computer music is and what is part of the craft. I want to basically try to find out what you should expect, for instance. So traditionally, composers expected to learn things in the conservatory, and the things that they would learn in the conservatory would be sufficient for all the issues in music. And clearly, that's not the case. And very soon, they find out that that's not the case. Then they go for a studio assistant. So, what's a studio assistant then? Well, you see that in many places, this is very common in continental Europe, especially. Don't see so much that in the UK, in Ireland, and maybe not so much in America as well. But it's very common in France, common in Italy, in Germany, and so on. So a studio commission composer, and the composer then finds that he cannot cope with the strain of figuring what the computer is supposed to do. He looks at the computer, tries to click a few things, can't do anything. So the composer then is assigned the obligatory studio assistant. Now, the assistant is someone that's very well versed in many aspects of technology and has a wide knowledge of techniques and things that make it pure music. A technician is someone who has a great eye and great ear and can detect things very quickly and basically construct the thing the composer then will decide to choose in his piece. The composer then is going to be crippled by these lacks of skills, and he will give control to the skilled assistant. So who do you think is the author of the piece in this case? This is a really interesting question because we find that many composers are well known for their electronic pieces or for electronic parts of their pieces, but the truth is that a lot that was written, or was composed, or was created by someone else. So, what we're trying to look for here is what would be gradus ad parnassum computer music. So, gradus ad parnassum is the very famous book on counterpoint by Fuchs. And when I refer to doing sound as initiation to composition, that's the link here. That's what I meant. So you can see that conservatory education really does not prepare you for computer music. It's clearly important, as you just see, it's a component in the whole makeup of the musician, the computer musician, the computer composer. but it's clearly lacking content. We also find that the technical skills that are needed really cannot be devoid. Not something that is devoid of artistic merit, and that's the key thing. Many composers will look at the and think that, oh, this is something that's not artistic, and I shouldn't be touching it, because if I touch it, then I become tainted. I become merely an engineer. And to start with, this is kind of a notion that is completely outdated, and that's something that we should be revising. So here, this talk basically try to go and define, or start to define, what the Gradus of Parnassus would be for your music. Although I find it is only a start, because there's so much that needs to be thought, and the field is not well defined yet. But really, we need to start try to find it, try to advance it in some way. So this is what I try to achieve in this talk. So is everything going all right? Can you see everything? Can you hear me all right? Okay, so Kari. Okay, so let's try to define the area of computer music, necessarily, or the area of electronic music, if you will. Let's concentrate that on computer music first. So the first one of the important first kind of defined discipline of computer music was made by Richard Brown in his Elements of Computer Music. He has a whole introduction to his book that tries to show what makes up computer music and what you need to go ahead. It's interesting. He cites, in order to define it, and in order to define the things that you need to do, he cites a very interesting. He makes a very interesting point where he reminds us about a lecture by Richard Feynman, who started the discussion after the lecture with an apology to the audience who knew nothing about physics or nothing about mathematics, because in order to discuss the area, you needed that and assume familiarity with those things. And so Moore is very clear about what is required in order for us to start studying, start discussing, start proposing music. He's quite clear about this. And his definition, we're going to explore a little bit of that later. There are very clear aspects that we need to note. Now, this is the kind of a very kind of an early attempt, which was made in the late 80s and 90s. Of course, there were earlier definitions of the area. I mean, even in Max Matthews' book, there are some ideas about this, but Moore's, I think, is the first time when these ideas are getting together in a definite way. Now, the next one that I mentioned is one that was prompted by the S2S fast action neuron, which was networking kind of a networking group that's set up in Europe back in the mid 2000s. S2S is sound, sound consciousness. So they put up a roadmap for sound and music computing, and in this roadmap, this is a kind of a roadmap, which is basically a set of goals and a set of attempts to define areas, to discuss things that we want to do, that we should be looking at if we're dealing with sound and computing. And of course, they have the SMC network, which is kind of this, this governance group that tries to set up the area, and it's quite strong here. In fact, we had the SMC conference this year in Minute. It was a very well attended, and there is a clear line there, but it's we're going to see a line that is very much linked to research in the first instance. Okay, so let's talk about the disciplinary context from the perspective of Richard Moore. He mentions this thing here. This quotation is really interesting from his book. Says that most academic disciplines are disciplines of thought. I quite like this idea, the idea of disciplines of thought, and the fact, and also mentions the fact that the computer is an instrument of the mind as well. The computer can act as instrument of the mind. But anyway, coming back to this, so most academic disciplines are disciplines of thought. They exist to define correct or useful a subset of human knowledge. Computer music, however, is strongly interdisciplinary. Therefore, a correct view is one that does justice to several points of view simultaneously. So this is the crux of the question here. If you want to work with computer music, you're going to have to be able to navigate a series of disciplines, not a single one. So musicians are often very much kind of dedicated and focused on their own discipline. This is not the thing, because ever since you're little, you learn an instrument, developing your knowledge of that instrument. Then you learn a little bit about other instruments, a little bit about music in general, and so on. But there is that you're actually very much single disciplinary, single focus. Whereas so computer music comes along and offers this whole area that you have to explore, and sometimes it's very hard to navigate it. And to exemplify this idea, we have Moore comes up with a map of. Now, this map is maybe not so complete today, but it's a good start to kind of try to organize the areas where we have to navigate. So here's the map, and this is kind of a screenshot of his book, of the figure in his book. So as you can see, it's kind of there are 5 corners to this figure. At the top, we see music, kind of the central position of this for it's computer music. But then you have this underpinning this, you have computer science on one side and psychology. Now, an interesting point of placing psychology as an important element here. We saw today, this morning, some examples of how, in practical terms, music and psychology can be feeding each other. In the examples of music therapy that we saw there, but there's also a deeper connection where the whole idea of cognition, which we see here in one of those triangles there in the middle, and music cognition. So how we perceive music, how music is understood, is really important for computer music, because it forms part of the tools that we have to create music and then to use computers to do that. But then the bottom, you can see giving the basis for the field, and I think it's really well thought out, this, because you can see engineering and physics forming the kind of foundations of this, in terms that of one side, the technological foundations of be able to create the devices, create the structures, create the software that we use, the tools that we use. And the other thing is the foundations, the theoretical foundations for the whole whole area which comes from physics. After all, we are immersed in the physical universe, and we perceive sounds are transmitted through, from sources to us through this physical universe, and there's the whole physicality and the whole idea of how sounds are created are the basis of it all. So you can see this figure is very well thought in terms of the basis, the foundation, and then the arms that strengthen it, and the width for the air, and then music is central of it all. And inside the figure, you can see various areas that you have to navigate. Now it might be impossible for us to be an expert on all these parts, but we really need to have a good grasp of these things, these ideas, in order to work with computer. So as we see, things it's fundamental for us to have some ideas of digital signal processing, some ideas of acoustics, some ideas of programming, and of course, likewise, music theory, composition, performance, and they are really important. And then other areas, having some knowledge of what is artificial intelligence, and what is psychoacoustics, and so on. It's very important. So Moore's principles are really sound, even though they might need to be updated to the configuration of knowledge that we have today. They're quite. Moving on, the next one is the SMC roadmap. So the SMC roadmap is a newer thing, and it's really is there to try to determine what the current challenges are to the discipline, and what the future scenarios can be. So we have cleared some roadblocks, things that prevent development, and it's really something that has an agenda that is research oriented. So it's a little bit more advanced to the principles that I'm talking here, which are very basic, very trying to define the area. And, they're mostly towards where we're going to go to. But two of these strategies and challenges that are listed in the SMC roadmap are really important to our discussion. So these are intensify interaction between the arts and clearly develop the interdisciplinarity that we are trying to foster here. It's really, really important. And it's very important that people involved in the arts are technologically minded and research minded, and people who are working in research in the area have artistic inspiration. And being able to design curriculum that is multidisciplinary. And I'm going to pick up this point here when I come to do our case study in a few minutes. So this is really important, to be able to pick up all the disciplines that we're talking about here, to be able to connect them and bring them into a curriculum that will form people without this different knowledge, these different areas. So from these discussions, then we can come up with some basic requirements, fundamental requirements for a computer music practitioner. Now, these are things that will underpin further study and can be built on to develop more work on music. But there are fundamental things that we really should be concerned with if we are to kind of embark on this area. So the first one is a simple one. It's an easy one. We really need to have sound knowledge of music theory, composition, and performance. It doesn't imply that you need to be a star performer or that you need to to be, because that's itself that might not be what we're looking, but that you need to have some understanding of the performance aspects and to have some experience of performance or something, and even and having some knowledge of what's called standard music notation, standard common practice notation. There's understanding of the development of Western music, and also the development of world musics, and understanding of ethnomusicology and so on, and sound music, and with one that is somehow devoid of all the pseudo kind of theorization that has occurred around. I mean, one music theory that is not biased towards any view of music, but is very objective one, and which I think we have there is that understanding of what today, and that's what we should look for. Moving on, the next thing is the sound aspect, the understanding of acoustics, and psychoacoustics, how we perceive sound, and the understanding of how audio technology can be used to can be seized on to basically transmit, record, transference. So some understanding of audio technology we're very well informed the acoustics, from acoustics and film physics, and from the perceptual aspect of sound as well. You see that there is also these are not pillars that are completely independent. There is some overlap, because some of the things we learn from one side are very important on the other side as well. But it's a key foundation of computer music. And then computer technology, as in understanding how computers work, understanding how hardware, the technology of the computer, and understanding how the basic software work, or how operating systems work, how the networking and so on, and an ability to do some programming at some level. We're talking about scripting. We could even go down to lower levels of programming, but some understanding of what programming can do for you. And this is very important. Fundamental mathematics. Now, this is, I think, and I'm not talking about here anything exotic. High school mathematics. You don't even need to go calculus, but it's important. Trigonometry, algebra. But if you have a bit of calculus, it helps as well. But things that are, 300-year-old mathematics, not much more than that. A bit 200-year-old Fourier transforms and complex numbers as well. But something that it's very something that it's not achievable, you can't, out of reach. It's very fundamental, basic. Anyone who was able to go through music theory would be able to achieve. So these are things that are really important, I think, and they are the fundamental pillars for in the study of music. They might be part of what we're calling the gradus ad parnassum computer music. Now, what I want to do now is I want to move on to give you a case study of a computer music program, an abstract computer music program that's not, hasn't been delivered. Bits of it have been delivered. I've delivered bits of it and I've delivered aspects of it. But this is something is used just to give context to discussion. What would be a computer music program that would build on this, that would deliver this type of education, this formation to a musician, and that will make computer music traditional. Now, note that I'm moving on from talking about composers to talking about to using the word computer music practitioner, and the reason for this is because I think that the word composer might be a little bit maybe out of date. The idea of a composer today is very much different from the idea of a composer in the 1950s. The idea of the big composer who was the sole mind that writes the score and this piece. The idea of the genius composer, which was something that had evolved from the romantic period. In the 21st century, this is certainly an outdated idea. So I prefer now maybe to just move on to talk about computer music practitioners. Anyway, so we can use a program like this. Now I bring C sound into the mixture. You can use this to use C sound as the main educational creative tool in this computer environment. Teach computer music, and of course this is something the main tool for production and performance and doing for practical use.
Dear
Once
Victor,
this is finished.
I'm sorry. We have to be close
Okay.
to the conclusion, if it is possible, please, to conclude.
Okay. Can I hear? Give me 1 minute. Can you hear me?
Yes, 1 minute. Yes.
Okay, can I carry on? Okay. So, do you want to? There's a lot of echo. I can't hear you very well. Shall I carry on?
Sure.
Okay. So here are basic sections of this course, this course. So we're looking at 5 sections. The first one being Introduction to Computer Music, and we'll see what that entails. That's a section that is to do just the programming, just music programming specifically. One that's to do with interaction and performance interaction. One that has to do with sound synthesis and processing. And the final one that links everything, some composition studies. And now, again, composition in a very expanded way. Okay, so let's have a look at these sections in turn. So what would an introduction to computer music be? Okay, so we need to look at the background of computer music. And there are 3 things that I want you to do with this. I would like to have a look at the history of computer music. This might start back with the beginning of the century with the dynamophone showing first electric instrument. And just a minute. Okay, so I'll carry on. Okay, thanks, Rory. So moving on, some music systems, which basically the variety of music systems that exist around. Next one would be technical foundations, which are basically technical foundations of the systems that we're looking at. And say if we take on C sound, then we'll look at technical foundations of C sound. Then music programming is something that will basically pick up a particular system and talk about that. So we have fundamental concepts of programming, so all the basic aspects of C sound. Looking at things like advanced data types that we have in sound. Looking at control flow, looking at signals and graphs, and user-defined opcodes. And this is very specific for C sound. Other systems might have different focuses. An interaction then. Let's carry on with the chosen system, C sound. We'll look at computer score. So what is a computer score and how you can manipulate it? How you can manipulate, how you can use media control to interact with the computer. How you can use networking to talk with computers. What is scripting and how you can use it for composition. So, and then in the final part of sound synthesis and processing, then we can, we can more generally apply the idea of sound synthesis, but we can use C-sound, for instance, as an example. So we have classic techniques of sound synthesis. We have time domain signal processing. We have spectral processing, Fourier transforms, and so on, and granular techniques, and we have physical models. So these are the 5 areas that we could talk on sound synthesis, and that inform someone to work with those tools. And then in composition studies, then we should look at different ways that computer music is composed. You have the classic fixed media composition, which is the way that traditionally have used the sound for. But then we have fixed media plus live performances also, and live processing of sound. Sound is being used for live processing quite a lot last 10 years. And then the ideas of improvisation, live code, and installations of, and web. This is something that is kind of exploding now in the idea of network of, and especially web-based music. Very important things. So to conclude now, we really need to understand that computer music in the 21st century is a world away from the big composer notion that lingered from the 1800s to the 20th century. This idea of the big composer is encouraged by traditional conservatory education. It's completely bankrupt and useless for the majority of aspiring musicians today. It does not account for fluid nature of music making that's taking place around us. It does not foster the learning skills that are key for embracing technology. And so I wanted to show a few pointers and the basic skills that we're lacking. And we have these 4 that are proposed as a knowledge moving ahead here. So we'll try to describe this up and now, so we start. And I think it should be an aim that a clear aim for us to define it and see what these emerging ideas and how they can be the foundations of the discipline. So that's it. Thank you very much.
Thank you for this paper. Unfortunately, we don't have time for questions, so please, Ian. Thank you, Victor. Thank you. Okay. One, two. So this is your mic.
Hello, everybody. My name's Ian McCurdy. I hope you can understand me. I come from Belfast in the north of Ireland, where we speak English, but sometimes it's not quite English. So hopefully you can understand me. First of all, I'm just going to fly straight into this because I know we're running a little bit behind time. Just quickly, I want to say thanks to Gleb and everybody at St. Petersburg for organizing all this for us. What I'd like to do here is, because maybe there's a little bit of an overlap with what Rory presented us with earlier. He introduced us to Cabbage and to some of the new features of Cabbage, but what I'd like to focus in a talk I've entitled Gourmet Cabbage is just some of the features that particularly I find interesting and that I feel are a little bit unique and show us ways into C-Sound, ways of interacting with C-Sound beyond sliders and buttons, the things that we already know about Cabbage. They're kind of other little hidden things that kind of allow us to interact a little bit more closely with the sound and to kind of open up the black box of C-Sound, because C-Sound in its traditional form is quite a black box. We can't really see what's inside until we hear what comes out. And sometimes hearing what comes out doesn't tell us everything. Sometimes that experience can be augmented in some way through the user interface. My experience with Cabbage started at the first C-Sound conference in Hanover, where I think pretty much Rory introduced Cabbage to the world there. And I offered to him at the time, I'll run through it all and I'll see if I can find any bugs. And he was actually getting a flight from Berlin back home, and I was getting the train back to Berlin. So on the train back, I kind of ran through everything and made a list of bugs that I found. And we met up in a beer garden in Berlin, and I think we started going through bugs then, and it's continued ever since then. But what I'm going to do now is just to demonstrate a few examples that will maybe illustrate some things that I find particularly interesting, and even sometimes features that I've requested, because with Rory it's great. I can suggest a feature request, and then within 2 hours it's there, and he sends me a new compiled binary with that feature installed. So some of these things he did specially for me, so I obviously feel obliged to use them after that. So the ability to display function tables is a big thing, I think. It's something that's very regularly asked for on the list. How do I display a table? And there was the built-in filter option, but it was really kind of a bit ugly and a bit clunky and didn't really show us very much. But this ability to interact much more closely with gen routines kind of really shows us what they do, and it suggests other possibilities as well. So for instance, we have a gen routine gen 19, which is it's supposed to be used for additive synthesis, maybe. But what I've tried to do here is just to kind of think of it not as a waveform, an audio waveform, but more like a kind of an LFO shape, but to modify aspects of the harmonics and the component of harmonics and the DC offsets of each harmonic and the phase of each harmonic. I mean, all of that sounds pretty grand, but really, when you see it, it just looks like a skipping rope or something like that. And so, by visualizing it in this way, it automatically suggests other compositional possibilities. So, if we can hear this. It's actually gone silent. I mean, what happens is this little bead kind of behaves in response to gravity and friction, if you can imagine gravity and friction within this system here. We'll try and G it up a wee bit here, because I can change some of these things here. That should help there. Basically, the faster it moves, the louder and more. And we can add in additional So I think this is an application we would never really have thought of if we just read the manual page and thought, what can I do with this gen routine? What's happening here is in order to reform the table, it has to be continually reinitialized. So there's certain restrictions in that. We probably can't use massive table sizes. It's going to slow the whole thing down. And we're going to need to peg the rate of reinitialization. So typically you do it maybe about 32 times a second, 16 times a second would normally be enough. Another method of interacting with tables and changing tables is to just change them value by value, which is going to be a much more efficient way of doing things if the situation allows for that. Let's suggest a new C-Sound user. They want some sort of a wobbly line, some sort of function which will modulate some feature of their synthesizer in some sort of way. It can be a bit daunting because there are many options suggested in the manual for creating some sort of a wobbly random function. But it makes it much easier to kind of really grasp what each of them does if we just print it out. So in the past, we just had to imagine what the random I opcode did, but now we can see exactly what numbers it's producing and compare that to or even creates a audio representation. And we can see also that if we apply some sort of a filter to the function that we have, because we can filter control signals as well. So as well as hearing the change, we're seeing the change, or applying a line 2 gives a slightly different sort of a portamento. Some of the sort of less well-known, less well-used ones can explore. Some of these ones are quite interesting that use a function table, but in the manual it generally suggests recommended to use a sine wave, but sometimes it can be more interesting to sort of mess around with these things and experiment with different waveforms, different mapping functions that they may use. Or even kind of Gaussian shapes. Okay, so we're just creating kind of jitter signals. We can kind of very quickly maybe find something that's going to suit what we're looking for. Just going to skip over a few things here. Just a kind of an oscilloscope to show us various waveforms. We all know what a sine wave looks like, but one question that pops up repeatedly on the on the C-Sound list is, why can't I just create a sawtooth waveform with a Gen 7, just kind of draw a picture of a sawtooth? But of course, the sawtooth that we listen to on an analog synth, it's never a perfect shape like the tooth of a saw. So, you know, we can very quickly explain what is actually happening with a band-limited sawtooth. We can see that there are certain high frequencies that are removed, and as we go higher, more of those high frequencies are removed. So perhaps this is something that is useful for a student to kind of very quickly get to grips with phase distortion synthesis, for instance. What exactly is happening? What is that distortion factor doing? What does it sound like, and how do we relate what we hear to what it looks like as a waveform? I think one of the most, or the two most interesting aspects that have been introduced very recently in Cabbage are the ability to view waveforms, but also the ability to track the mouse position. And we can use this to kind of then interact with widgets in a way that's not really intended by the author of Cabbage. We can kind of think of our own ways in which to do that. And if we can see the waveform on the screen, we can then interact with specific points in the waveform with the mouse. So for instance, in this one here, it's a mincer, which uses FFT to allow us to replay a waveform with complete independence between time and frequency. And we can use the X position and the Y position independently for different things. We can use the Y position also for transposition. Or we can create little regions as well on the waveform and then play that region. Another feature that I think is quite powerful, I think I'll just open another example, just show this. And is that of adaptive GUI. I'm always put off when I'm confronted with a GUI with 200 controls and sliders, and none of them seem to do anything. Sometimes, you know, we're all a bit lazy and we don't want to have to spend an hour trying to figure out what each thing does. So if we can minimize the number of controls that we present to the user and even adapt the GUI according to certain functions that we have chosen, because in certain modes, certain controls may no longer be relevant. So in this one here, we can change certain modes. So to use a kind of a manual pointer mode, or in which case speed is going to be irrelevant, but if we choose speed mode, then we're going to need some of those controls. So I think that helps people as well who don't really want to. We are all a bit lazy and we don't want to read instructions. I do provide fairly extensive instructions at the top of most of these things, but I'm not sure to what extent everybody actually takes the time to read them. We can start even with no GUI at all. I like these things that are kind of a little bit, that subvert the idea of what we do with these things. I think the first things we tend to do when we have a new front end is to build a digital delay or a filter, kind of things that exist already in hardware or exist as VST instruments. But I think the whole point of using C-Sound and using this fantastic open source software is that we do try and explore things that don't just imitate the commercial versions of that. So with this one here, there's no GUI, and the GUI elements are actually created just out of graphical elements, just little squares. But by using mouse tracking, then we can the little bars then they get darker according to the intensity of that partial. Or we can just very quickly draw. Which is probably a more maybe it's a more inspiring experience than just looking at the generic sliders that you would maybe see in all GUIs that everybody else draws. So I think that becomes part of the creative aspect to working with this, is just to think about the user experience and will it inspire them to when they see the GUI, or will they just be terrified of this kind of mass of knobs and buttons with descriptions that don't really seem to explain what they do. A sort of slightly silly little thing here. This is maybe if anybody's learning the guitar and they want to just practice a few chords. But it demonstrates a few other features that Rory has introduced since the Hanover conference. One of them, I'm not sure if this one's going to work here now, but the ability to use presets to change things. And there, it's not going to work. It's probably going to play a C major. Yeah, we need to talk about that later. These are actually checkbox widgets, but what it does is all the checkboxes on a single string are radio buttons. So that means that when you press one, it turns off all the others, which is kind of what you want. You're on a guitar, you're not going to fret on the same string more than once. And the other thing it does is it uses the visibility of widgets as well. So all the other checkboxes on that string are then deactivated whenever I activate a new one. Don't know what that chord is. Okay, am I okay for time? Am I okay for time? Yeah. Yeah, I'll show you a few other things that are they're a bit fun, but there also is a sort of a serious element to them, semi-serious. Sometimes I'm also interested in just kind of stress testing some of the things that Rory introduces. So when he introduced this ability to kind of change the appearance of widgets, he probably doesn't really intend that people do some of these sorts of things. But I think it's maybe worth just pushing it just to see what we can do. So again, each of these is just an image widget, which is being animated by sending instructions to change its location on its ident channel. And it's just as you can see, it's a little ball bouncing around. And of course, we've a number of controls here. But I wanted to kind of bring in some sort of element of physical modeling in a very loose sense by changing the shape of objects in order to change their sound. So it's basically just FM synthesis, but we're changing the parameters of that FM synthesis by changing the dimensions of the object. So as a sort of a long straight line, it resembles a string, sort of. As a sort of a taller object, it becomes kind of more metallic in sound. A square block will maybe be a little bit like a wooden sound. So we can kind of design instruments that will play sort of a scale of notes. And we can play around with physics a little bit as well here, the damping that the ball experiences when it hits the ground. So there's a little bit of a sort of challenge of the idea of how to think about the parameters that we use in synthesis. And also in how we think about the generation of note events. We're getting away from thinking about bars and beats and crotchets. Some of these things are maybe good for if you need to entertain some young grandchildren or nieces or things like that. Again, just another one which is using the animation of widgets. In this one, the idea is that we have to burst these bubbles just by clicking on them. It's not terribly difficult. Let's see. But there is a compositional side to this in that the higher up the bubbles get, the higher the note gets. The larger the bubble is, the louder it will be. So you can either just approach it as a game in which you have to burst as many bubbles as quickly as possible, or you can think about creating certain musical phrases according to where they... And it does actually get harder if you are persistent enough. They get faster and more plentiful. This also uses Rory's feature of creating widget arrays. So we don't need to create each of the widgets independently. We can just say in the code, do we want 10 bubbles or do we want 50? If you can manage that many. But when I first, sometimes when I write these things, I send them off to Rory, say, what do you think? And I sent this off to him, and about an hour later, he said, whoa, I got 200, but I need to do some work now. So I kind of feel a bit guilty distracting him sometimes with these things. But. I don't know if you can see this on the... Oh, you can, just about. It's a little bit annoying sounding. Well, I was annoyed by a mosquito in my hotel last night, so it sort of reminds me of that a bit. It's basically just a swarm of flies, and if we click on it, we splat them. But we can change certain things about these flies. So excursion is just the distance that they will population number of flies. But there is as I said, there's just sort of a serious side to these things, and it's just a synthesizer, you know. And by increasing the number of flies or reducing the number of flies, we're adding or reducing the number of layers within that cluster. And by changing the fly size, we're changing the pitch, the basic pitch. By changing the excursion, we change the amount, the frequency. Excursion that each fly is likely to make. I like to think that if Xenakis was around today, he would be doing things like this. So he had these ideas, but he just didn't have the software just to quite do stuff quite as advanced as this. So that's maybe I'll just wind it up there. I kind of left a few things out just so that we could maybe catch up a little bit. But if anybody's any questions or comments, like either to me or even to Rory, I'm sure. Questions? Yeah.
Another microphone, please. I'm sure there's a lot of questions too. Yeah.
Just about, by the way, if a lot of these examples already exist within within Cabbage itself, just in the examples section. But if you want the most up-to-date, you can get them on my website as well. There might be a few more there, and they're there.
Okay. Any questions, please? Anton?
Well, how do you program the graphics? Is it? I'm interested. Is it?
You want to see some of the?
Is it built in, or it's some specific language?
It's well. I'll show you the code here quickly. Oh, this is all of the GUI code is there. That's all it is. Each of those things is just the number box for allowing us to modify aspects. The little flies themselves are all created with a single line of code there. You can see that we're creating a widget array 50, so there's a maximum 50 flies. And that's very efficient, but we do then need to do a little bit more within C-Sound. We have a little bit more control. Once we are able to modify these things in C-Sound, we can use any function, LFOs or random functions, to move things, change their colors, hide them, show them.
You create the image, and you can with C-Sound update the parameters.
Yes.
Oh.
Yes.
Oh.
It's just, I think Rory showed you an example where you create a string message, and that string message might be something like move to this point in the screen, and then you send the widget that message and it moves to that point in the screen. But you do it 30 times a second or 20 times a second, and it looks like, it's like animation.
So here C-Sound becomes a graphical engine also?
Insofar as it's sending instructions to a front end that is capable of producing those graphics.
Oh, thanks.
Any questions on this? Sure. Alex?
Yeah, thank you, Ian. Amazing what you do there. And my question is like the communication between Cabbage and C-Sound. This is via channels. Now I see the code. Now I have more ideas. But
it's via the ident channels. Yeah.
okay.
Yeah.
Great.
It's probably not intended for these sorts of things, and I always have a conversation with Rory and say, look, this is probably not the way to do stuff like this. But I do like the idea of something being completely encapsulated within one program. And I think that a lot of the examples I did in the past with the filter widgets, which were good in their day, useful in their day, but they're kind of quite outdated now. But people still use them, and I think it's just because there's some people they like something which is part of the core program. So
it's a way because of C-Sound Qt, you also used to use channels to communicate with the widgets. So
yeah,
it's like yeah. Thank you.
Thank you. Any questions? Okay. Ian, thank you for a very bright presentation. Thank you again. And right now we have a short break. And after we continue our amazing ICSC conference.